questions.
Could you take them
Questions. Yeah, you Aditya, you cannot raise your hand and talk. Okay, where's the chat here? Let me sort of see. Chat. 8. Okay, 8. Okay, any other one, Max?
Can you take up 7 too? Because I don't know if my answer is right.
Yeah, so 7. I didn't give the answer, right? Did I?
Yeah. No.
So 7 and 8. Okay, anything else? So just 7 and 8? Okay. So let me see here. 7. What was 7? Okay, so the skier. Okay, let me admit Matthew here. So coasting down a hill, that is okay. Blah 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 blah. Skier's speed near the top. Determine the speed of skier's travel. Okay. All right, downhill. All right, so let's do this. Hold on a second. So let me share the screen. Zoom back. All right. Okay, so what do you have in number 7? So number 7, we have like someone on the slope and a certain angle. What's the angle again, guys?
23 degrees.
How much?
23.
23 degrees. We have this skier here. There you go. Spool. It's a big toque. All right, and does he have initial speed?
Yeah, it's 3.5 meters per second.
3.5 meter per second. Okay, what's the mass?
It's 61 kilograms.
62 kilogram. Okay, good.
61.
61, and it goes downhill for how long? Not for how long, but what's the distance?
62 meters.
62 meters. All right. So that's what you have here. So this is delta D here. Okay, and they want to find the speed at the bottom. Is that it?
Yeah.
Yeah. Okay, and there's friction. Is there friction on this?
Yeah.
Yeah, it's a force of 72 newtons.
72 Newton.
Mm-hmm.
Okay, so let's do an FBD here. So what do we have here? So let me put my vertical and horizontal. Matthew, okay, hold on a second here. There you go. Okay, so let's do an FBD right here. So what do we have? We have, of course, the weight. All right, I'll put FG here. We have the normal force from the slope. We have the friction, which is the opposite. And that's it. And then on top of this, we're going to put the directions. So the direction is like this, right? And this is going to be 23 degrees, right? Right? So you're going to use, of course, like you're going to use the work energy theorem to solve this. So the net work on an object is equal to the change in kinetic energy. You can sort of figure out what the initial kinetic energy is because you have the initial speed, you have the mass, so you can find this, all right? So Kf here will be equal to Ki plus net. And of course, you can, once you found the kinetic energy, final kinetic energy, you can isolate for the speed, right? So what you need to find here is you need to find the net. So you could find this. So we need to find the net work. So the net work will be equal to the work done by individual force. So the work done by normal force plus the work done by friction plus the work done by gravity. All right, so right away there's one that disappears, and it's this one because it's 90 degrees perpendicular. Normal force never does any work. And then, so what you're left with the work done by friction, which will be like F times the distance, right? So the distance here is 62 meter right here. The friction is this. And the angle between the two is, of course, 180, right? So it's going to be like cos of, whoops, going to be like cos of 180 degrees plus gravity. So gravity is going to be the force of gravity, which is mg times delta d times the cos. All right, well, what's the angle between gravity and the displacement? Is this here. And you can see here that this angle here will be equal to 90 degrees minus 23 degrees. So it'll give us 67 degrees. So here it's going to be 67 degrees. So you plug everything in. So this one is going to be negative, of course, right? So this is going to be like negative, like 72 Newton times 62 meter plus 61 kilogram times 10 meter per second square times 62 meter times cos of 67 degrees. So you find what this is equal to, and then you put it back here, and then you're going to find what the speed is. Is that okay? Is that good?
Yeah.
Yep. Yeah. Stephen, what's the answer you found for 7? Stephen Lee, are you there?
Sorry, I have to talk to my family. What's that? Sorry.
No, you cannot talk to anyone else.
My mom's in back. Sorry.
Okay, so what's the answer for 7? What did you find? Stephen. Okay, Timothy, what's the answer for number 7?
I got 24.87 meters per second.
Okay, is that what you got, guys?
I have no idea. Could you tell me how you got that?
Well, you just plug this in here, like Timothy. Did you do it like I did?
Yeah. So your total work would be 19,241.45 joules, and then
19,000.
I think so.
That's not what I'm getting right now.
Wait.
I got 10,313.
Okay, all right.
Oh, I might have done a calculation error.
I have no idea.
I got 19 meters per second.
I got what Joe and Forrest got. I got 18.72 as well.
Okay. Well, don't forget here, I don't know, like if it's like close, some people might use like 9.8 here, right? Instead of 10, but okay. Anyway, so I'll let you figure this out here, but I'll try to sort of find the answer at some point and put it in the board, okay?
Okay.
All right, so let's look at number 8. So Aditya asked me for number 8. So what is number 8? A high skater of mass, okay, a high skater of mass 55 falls and slides horizontally along the ice. Okay, the coefficient of kinetic friction of the skater in the ice is determined using the work, the skater's speed at the instant the slides begin. Okay, so let me see here. So this ice skater right here. Okay. Okay, ice skater, so you know the mass. Hold on a second, I'll put it on, oh, you should be able to see this. The mass of 55.2 kilogram. So the distance is 4.8 meter. So he stops, so right here. So its speed is 0 meter per second. The coefficient of kinetic friction is 0.27. And you want to find the initial speed of this. All right. Okay, so use, of course, the work energy theorem as the mentioned. Where's my? There we go. So let's do an FBD here. So FBD, Fn, Fg. There's no friction on this, so there's no friction, right, on that? Is there friction?
There's
There must be
kinetic
friction.
friction.
It slows down. Where's my friction? Oh, it's right here. Sorry. There's a friction, and it'll be like kinetic friction. All right. And then we're going to put this one right here. Okay. All right. So the network. So network will be the work done by normal force plus the work done by gravity plus the work done by friction. And of course, these are 0 because they're 90 degrees perpendicular. So the network is nothing else but the work done by the force, friction. So it would be this times cos of 180 degrees because the angle is indeed 90 degrees, 180 degrees. So that'll give you, of course, this. And then knowing that the coefficient of kinetic friction is equal to Fk, times this here. So so Fn, of course, will be equal to no, it's not Fm. What am I doing here? So you want to find like so Fk here is, of course, is going to be equal to Fg, right? Because there's no other forces. So it'll be equal to the weight times this. So it'll be equal to mg times this. So you put everything in, so you get that. All right. And yeah, so you put like the values in. It's negative, and then you use like network energy theorems. It will be Kf minus Ki. So this one is 0 because the speed is 0. So what you have the initial kinetic energy is equal to this. And the net work is equal to that. So there's 2 negative, it turns into a positive. And then what you get is you get that. Okay, equal to mvi squared over 2. You can see here that the mass doesn't matter. It goes away. And then like uvi here is just equal to like 2g uk times delta d. And you plug everything in, Aditya, and that should be okay.
Thank you.
Are you good? Yeah. Any other questions? No? Okay, is Catherine around? Catherine, are you here?
Yeah.
Oh, okay. Good. All right, so let's continue. So yeah, oh, he's always like, okay, there you go. So someone else wanted to come in. Okay, so let's start with the lesson today. So today, what I like the homework, it's not all on the website. So I'll put like there's one thing that I need to upload on the website for today. So just wait, like probably like in the afternoon, I'll upload something, and it's a problem that you can work on. Okay, it's going to be a little bit similar to what you learned yesterday. and then there's some additional questions, okay? All right, so let's start here. So we learned about the fact that energy is the ability to do work. We found like the very first type of energy is kinetic energy. So when something has kinetic energy, it can perform work, all right? The other type of energy besides kinetic, there's three types of energy, three categories. There's kinetic energy, the other one is potential energy, and the last one is radiational energy. We're not going to talk about radiational energy in high school, okay? We're going to sort of focus mostly on kinetic and potential energy. All right, so potential energy is the energy that a system has by virtue of its configuration. So I'll write it down in a second. So what does that mean? Here is this. Let's say here I have, let me see here. I don't have anything. Okay, so let's say I want to destroy, I want to flatten this piece here. So I need to perform work on this to flatten this piece of paper here. What I can do in order to do that is I could use a heavy object. It should be like heavier than this, but a heavy object, right? And I can hold it at a certain height above. This object here has what we call potential energy, gravitational potential energy. Remember, potential means like it has the capacity to do work, right? If it were released, that's what potential means. So this object here is storing gravitational potential energy by keeping it at a certain height. And then when I release it, this gravitational potential energy is released. And as I release it here, it's going to come down. The potential energy here will be converted into kinetic energy. But the key point here is that when it falls, if it's like high enough, when it falls on this piece of paper, it'll be able to do work on the paper. It'll be able to flatten it. All right. Now let's look at some of the factors affecting this, what I call gravitational potential energy. Now, if instead of using this stapler, I were to use something much heavier, I don't have something, there we go. If I were to use, instead of the stapler at the same height here, if I were to use this big, thick book right here, all right? Now, which one do you think will have a greater ability to flatten my, my piece of paper here? Is it the stapler or this? Okay, raise your hand here, Aditya.
The book,
Yeah, why?
it has a greater mass.
That's correct. It has a greater mass. All right, so it has a greater mass here than the stapler. It would have a greater capacity to do work on this piece of paper. Very good. Now, second case here is this. So I have this piece of paper on the ground here. You cannot see it. In one case, I lift this book to a certain height. In the second case, I lift the same book but to a higher height. So in which of those two cases do I have a greater ability to do work? Yeah, Madav?
When the book is higher.
That's correct. When the book is higher up, it has greater ability to do work. Well, you found right away, you found like the factors that affect the gravitational potential energy. It depends on the mass of the object and on the height. Now, it's a little tricky here. I'm going to sort of explain a little bit more here. Okay, so let me sort of go back to sharing the screen. My poor computer. It's an old computer. I can sort of hear like the fan going crazy. All right. I think the board should sort of pay me a new computer, using my own computer. All right. Okay. Let's do this. All right. So potential energy. So you ready? All right. So potential energy is the energy possessed. I don't know if there's two S all the way. Possessed. Is there one S here, guys, or two S here?
Two.
That's right. That's right.
There's two all throughout? Okay. Is the energy possessed by a system? That's very important here. It's not a single object. By a system, by virtue of the relative position or shapes, by virtue of the relative position of shapes of each object in the system. All right. So the relative position once again, if you want to ask a question, just give me a shout here. Relative positions of each object in a system is called the configuration of the system. Let me put it here. It's called the configuration of the system. Now, what it means here, it means this. Potential energy can never be possessed by a single object. A single object can never have potential energy on its own. Okay? It always comes as a result of interactions with other objects in the system. All right. So a potential energy can never have like potential energy on its own. It always comes as a result of interaction with other objects. Now, for grade 11 or also grade 12, for most cases here, we're gonna ascribe potential energy to a single object, but that comes only in a special case. That comes only, well, I'm going to sort of tell you in a second. Okay. Right. So,
Sir,
yeah.
does potential energy have like a little like subscript for itself?
Oh, yeah. Yeah, I'll give it to you in a second.
Okay.
Okay. Just wait. Okay. Well, yeah. Okay, so let me give it now. Potential energy. The symbol for it. In some books, it's going to be written as EP. As you may know, I do not like another subscript, so I use a different different symbols, which is used like, you know, in most books except like high school books. And all right, U. So U is called potential energy. All right. So let's look at gravitational potential energy. Okay, so which is UG. So UG. So let's have like our famous apple right here. Oh, let's maybe put it in. There you go. This is the apple right there. And let's have the earth right here. Earth is brown. Not find brown here. I'll use, okay, this is not to scale, of course. Well, so this is the earth. Make sure you make a real nice, I know there's a way for me to make a, oh, I guess it's here. Let me see here. Dun. So how does it work? No, how does it work? Symbol, open, shape tool. Ah, anyway, I'll ask my daughter later how to do that. Okay. Okay, so this is the earth here. Make sure it's right. And it's going to be the center of the earth. Now, the distance between the center of the apple and the center of the earth, we're going to call this the separation distance. Okay, going to call this R. We'll go with this R. Now, so when I hold an apple, this is not an apple, it's stapler. When I hold an apple at a certain distance from the surface of the earth, from the ground, it's not only the apple. Actually, it's not the apple that has gravitational potential energy. It's the apple and the earth. It's the apple and the earth together. And I'm going to sort of show you the real gravitational potential formula of for the apple and the earth. So the gravitational potential formula is this. So where m is mass of the earth, Little m is mass of apple. And remember G, what was G? Did we find G? Yeah, we did, no?
Yeah.
We talked about gravitational acceleration, right?
Mm-hmm.
Yeah,
So should it be R
it's
squared?
the universal gravitational constant, right? So universal gravitational constant. All right. So this is the real formula. This is the formula for the gravitational potential energy of the Earth and the apple. It's never on its own. An object can never have a potential energy on its own. It always comes as a result of an interaction with different bodies in the system. So here it will be like the configuration of the system will be where the apple is located, where the center of the apple is located with respect to the center of the Earth. So this is a relative position of the two, right? And the mass of each. Now notice here that it's negative. It's okay for potential energy to have negative values. Unlike kinetic energy can only be positive, but potential energy can be negative. And as a matter of fact, potential energy is meaningless. The only thing that we care in physics is the change in potential energy. That's the only thing that we can measure, okay? The only thing we can measure. I'll talk about it in a second. All right, so let me stop sharing. Yeah.
For the formula, should it be R squared?
No, it's not R square. That's the gravitational acceleration has R square, but now it's inversely proportional to separation, not square. That's a good question. Okay, I'll come back to this. Don't worry. Okay. Now, so be with me here a second. We talked a little bit about that before. Let me just, okay. All right. Okay. If I let go of this, you remember here that if the Earth is pulling this down with a force of, say, 2 Newton, this object is also moving the Earth up is pulling the Earth up with a force of 2 Newton. Remember that. However, when I drop this down, the Earth is not going to move much, right? It's not going to move. You're not going to be able to measure like the acceleration of the Earth. Although there is one, but you won't be able to measure it. It's too small. So this is why, in this case here, when I talk about the gravitational potential energy of the staple in the Earth, I'm going to ignore the Earth. I'm going to sort of ascribe all the potential energy to this object here. But you have to bear in mind, once again, that potential energy is always, an object can never have potential energy on its own. It always comes as a result of interaction with other bodies. But since here the Earth is so much more massive, it hardly moves, then we ascribe all this potential energy to this little object here, okay? So, let me sort of share again. Let's go back to this. All right. So when the change. So if I let go of this apple, it's gonna sort of move towards the Earth, and the Earth, of course, will move towards the apple, but hardly, right? You will hardly be able to see this. When the change in separation distance all right, so this is called delta R. All right, so when I let go, like this separation distance will change, right? So when the change in separation distance delta R is very, very small, very small compared to R. All right, so when I take an object here, I make it go down. All right, when it goes down, it falls perhaps 2 meters. Well, 2 meters, it's nothing compared to how far it is from the center of the Earth. All right, so this delta R here, which is 2 meters, is really, really insignificant. All right, so when the change in the separation distance delta R is very, 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 very small compared to R, then we can approximate the change in gravitational potential energy All right, so the change in gravitational potential energy would be this as you familiar with this approximation symbol here? You know what this means?
Yep.
Right? Yes?
Yes.
Yeah, okay, thank you. It's equal to that. Whoops.
Sir, are we allowed to use like the equal sign of the dot?
Yeah,
So-
sure, but it's, yeah,
Okay.
sure. It's equal to this. Right, where delta change height is the change in height of object, or smaller object, right? Less massive object. Okay. So from now on here, the gravitational potential, the formula for the gravitational potential energy is going to be this. Here's your object right here, M. This is H right here. And the gravitational potential energy is equal to this. All right. So this is the gravitational potential energy formula that we're going to use, where we'll not use this one. We'll use this, well, yeah, we'll use only that one here. Now, mind you here, this is true only when the height is very, very small, when the change in height is very small compared to how far the object is from the center of the Earth. You could not use this formula, for instance, if you have an object, let's say this stapler here, I were to hold it like, let's say 2 kilometers above the surface of the Earth, and then let go of it, all right? You should not sort of be able, you should not be able to use this formula here. It'll be like not exactly exact. You would have to sort of go back to this formula right here. It's a little bit laggy here. I can see here that, there we go. So you could not, so this is the exact formula. It's true in all cases. But if I were to drop an object from 10 kilometers above the surface of the Earth, this is the formula I should use and not this. But for all intents and purposes, we're going to use this. Okay. All right. So I'm going to let you like figure out here that this gives like a unit of joule. All right, mass is kilogram, G is meter per second square, H is in meter, so you got meter times meter per second square is meter square per second square times kilogram. Same unit as kinetic energy, so it's in joule. All right, it's in joule. Okay, so now let's have a, let's have an example here. So let's say here, it's the ground. This is table. All right. And here this is going to be, let's see here, there's a book. That's a book right here. And let's say the mass of the book is 2 kilograms. I'll put it in a second. So there's a table right here. And the table is 2 meters high. And let's say here that you have a pole. What time is it? 11:17. Here we have a pole. And let's pretend here that the height of the pole is 3 meters. All right. So the mass of the book will be, let's say, 2 kilograms. Now, a little bit later on, okay, so who's this here? Chat, yeah. Yeah, that's a tall table. Yeah, it is. Yeah, it is tall table, Max. Okay, so let's see here that the book finds itself on the ground. All right, for whatever reason. All right, so it's on the ground here. All right. So what I want you to do now, I want you to make a table. Just wait until I'm done, like drawing the lines. So you're gonna have here. You're gonna have reference level. Here it's gonna be the ground. And here it's gonna, well, sorry. Here it's gonna be the top of the pole. So now we're gonna put here, we're gonna put the initial UG of the book. Give yourself like some space here, okay? Because there'll be some calculation here, so some space here. Okay, there'll be like 3 columns. There'll be like 3 rows here. There'll be one here, there'll be another one here, and there'll be another one here, okay? Okay, so let's look at the initial gravitational potential energy of the book. All right, so initially, if we use like the ground as a reference level here, what is the initial height of the book? Anyone? Raise a hand. Can I see your hand? Yes, Max?
2 meters.
2 meters, that's correct. So the initial, it's 2 meters. So let's find the initial gravitational potential energy. So what I'll do here is I'll move the G on the top. So it'll be initial, the bottom, G on the top here. And it's going to be equal to mghi. Remember, that's our formula here, right? So right here. So we're going to use only this formula all the time. All right, so I guess I'll need like a bit more space eventually. All right, so let's put like the value here. So the book is mass 2 kilogram. So 2 kilogram times 10 meter per second square times 2 meter. And that'll give us 40 joule. All right. So this is the initial gravitational potential energy of the book. Now let's find out the final gravitational potential energy. All right, so when the book is on the ground here, what is the height of the book? Aditya?
Just 0.
0. So 8, whoops. So HF is 0 meter. So the final gravitational potential energy is 0. So final gravitational potential energy is mgHF, which is 0 joule. All right. All right. So now what we're going to do here is we're going to do the same thing, but now we will use the top of the pole as the reference level. All right. So let's look here at the reference level. If we look at the initial position of the book here, what is the height of the book with respect to the top of the pole? Stephen.
Is it like -1 meter?
Are you asking me? I know where it is. I'm asking you.
Sure, sure.
So what is it?
-1?
Yes, that's correct. So according to the top of the pole here, the book is actually down, right? It's 1 meter below the pole. So the height is -1. And now we're going to sort of find the initial, right? mghi. So it'll be like 2 kilogram times 10 meter per second square times 1 meter. Whoops. And I don't have a lot of space here. All right, and that'll give us this. So the lesson here is that, first of all, potential energy can have negative value. There's no problem with this, unlike kinetic energy. Now, what you can see here, you can see that the potential energy depends on the reference level. All right, so according to ground, it's 40 joule. According to top of the pole, it's -20 joule. All right. Now let's find the final gravitational potential energy. All right, so when the book is on the ground, the final height is, of course, -3 meters, right? So if we find if we find the final gravitational potential energy, so mgHf, it'll be 2 kilogram times 10 meters per second square times -3 meters. So that'll give us -60 joule. Ha! Okay. In physics, the potential energy is meaningless. We can never really measure the potential energy of a system. The only thing that we can measure is the difference in potential energy. Only this is measurable and meaningful. Now, the last part in this table is we're going to sort of find the difference in potential energy. All right. So here, the change in potential energy. Okay, almost done. So delta UG. Well, let's find this. So when the ground was the reference level, so the difference is the final gravitational potential energy minus the initial gravitational potential energy. So what was it? It was like 0 joule minus 40 joule, and that gives us minus 40 joule. So the book, by going down, has lost potential energy, gravitational potential energy. And you know that by losing height, it has a lesser capacity to do work. So that's why it has lost some potential here. However, if we do the same for the top of the pole, what are we going to find out? Well, let's do this. So the final was minus 60 joule, minus 20 joule. And lo and behold, it gives us the same value. All right. So what we've learned here that even though the potential energy is different, I mean, if I ask you what's the potential and gravitational potential energy of a certain object, you can give me like any number. You're probably right, depending on what your reference level is, right? But now what we've learned here is that only the differences in potential energy has meaning. So only, and no matter what your reference level is, the change in potential energy will always be the same. All right, so only differences in potential energy is physically possible. It's physically measurable. Potential energy is measurable. All right, so that's the key point here. You good?
Wait, sir.
Yeah.
So for the part, so you write like UFG. Are we allowed to write all of the little subscripts at the bottom? So I write like
yeah, the I and the F should always be. You mean like put the G on the bottom too?
Yeah.
No, just put it on the top. It's easier. right? I don't want you to put G like comma F. That's why you can put it up.
Oh, okay.
Key questions? All right. I'll come back to this. Don't worry. I'll stop sharing it for a second here. Okay. So we've looked at gravitational potential energy. There's another type of potential energy. We'll have also electrical potential energy, magnetic potential energy. We'll look at this a little bit later on. Okay. The one I want to talk about is the spring. Oh, I forgot to mention this. I'll write it down. Potential energy is an energy can be stored for later release. All right. So if I keep like this object a certain distance, I'm storing gravitational potential energy, and it has the potential to do work provided that I release it. A spring can also store potential energy, and we call this potential energy stored in a spring elastic potential energy or spring potential energy. If I extend it, all right, and I keep it there, I'm storing elastic potential energy. Right? If I were to put like a little thing at the bottom here, all right, and to keep it like, let's say there's a little object here on the hook right here, and I keep it like this, if I let go, it'll be able to do work on this little piece, accelerating the piece, all right? So whether I compress or I stretch, I'm storing elastic potential energy. Now, to be technical, it's not only the spring that has elastic potential energy, it's me and the spring. Both me and the spring have elastic potential energy. But of course, when I let go of this, the one particle that's going to move, it's the spring. It's not me, right? Because I'm more massive, much more massive than the spring. So that's why here, like when we talk about a spring, we ascribe all the spring potential energy to the spring alone, okay? Not to me as well. Even though technically it's both me and the spring that has elastic potential energy.
Wait, sir.
All right, so the last point here. Yeah.
So does that mean like so if you like pull a spring back and you let go, then your hand is technically it's impossible to stay still and always moves. It just can move by a really small amount.
Yeah, well, it's because you release it, right? You move
Yeah.
your hand away. Is that what you're saying?
Oh.
You release both hands at the same time.
Like so what I mean is like so it's impossible to like stay completely still while you release the spring, right?
To remain well, I mean technically the spring exerts a force on me, but since I'm much more massive, I'm hardly going to move. Like there's other forces also on me, like there's friction between my shoes and the ground, and so I'm going to hardly move. It's going to be the spring or whatever is very less massive attached to the spring that was going to move, right? Okay. Okay. So elastic potential energy. So the last one here. So oops. Yep. So elastic potential energy or spring potential energy . All right, so the symbol for this is ES. I don't use E because E is reserved for electrical. It's pretty easy. Oh, well, I made a mistake. Not ES. U. There we go. U. So the formula is pretty easy. It's this. Where K is, of course, our spring constant. Delta X is the amount of compression or the amount of extension, right? So if you compress the spring like twice as much, you're going to be storing 4 times as much potential energy, right? And the last point is potential energy is an energy that can be stored. energy that can be stored. Stored, all right, for later release. Okay, you cannot store kinetic energy, but you can store potential energy. All right. So questions?
Is there a reason why this formula and the kinetic energy?
Kinetic energy?
Yeah, are like really
Yeah,
similar.
it's the same form. Well, it's a good question. I think it's mostly like a fluke here.
Oh, okay.
Yeah.
Sir, how does the gravitational potential energy formula and
The real one?
well, all those problems, the real one, yeah.
This one?
Yeah, the real one.
Yeah.
How does this formula and the applications for this differ from what we learned earlier with calculating FG and using the formula with the R squared value underneath?
Yeah, I'm not so sure like if, what do you want to see exactly here? So just repeat it.
How does this formula and the
Yeah.
problems that we use this formula for,
The gravitational formula? FG?
how are they different from the other thing?
How? Okay, so let me see here. So I'll put something. Don't write this down, guys. So you're asking me here, how is this different from this one?
Yeah, and when
Well,
would we
it's different.
use each different formula? Like what kind of problem?
Oh, you would use this one?
The two formulas you just wrote down, FG is
Okay,
equal
so this
to
one here,
GMM.
like this one here, you use, once again, you use, can use it like anytime. Yeah, and then when you're dealing with problems where the object doesn't like change much height, you can sort of say that this is equal to mg here, where g is equal to this here, like gm over r square. Okay. Okay, let me sort of tell you here. So like this problem here. So if you were, let's say you want to design a missile, intercontinental missile, right? You will not use this formula, right? You will use the real formula because the missiles here will go over very long heights. Will go like very, very high. So in this case here, this is no longer the case. You cannot use like MGH. What's the derivative to what? Is that what you, oh yeah, is that what you want me to, yeah, I mean, I don't want to get into this here, but yeah, if you have a force, not all the force here, that's what, it takes us like a little bit of field here. The force is equal to, I think is negative. I think it's negative of the derivative, right? So if you take the derivative of this function here with respect to r, and then minus, you're gonna get your gravitational formula. Is that what you want to know? But I don't want people to know that. Okay, that's something like, it's the other way around. Is it the other way around? Yeah, it's the other way around. That's correct. You're right. It's the other way around. Yeah. Yeah, that's correct. Yeah, it's U is equal to this over this. Yeah, that's. No. What are you talking about? No. If I derive this, no, I got it. So it's F. No, F is equal to this. All right. So if you derive this here, it's r minus 1. So you derive this, you're going to get like r minus 2. All right. Okay. So what I'm going to do here is, so today I will upload a little bit later during the day. I will upload a problem. So do the problems. It will be like something on the work energy theorem. Okay, and I think you may have like a couple of other questions to answer. Let me sort of go and see here. Yeah, you got quite a few. Yeah, so 29 to 33, 36 to 40. Ooh, that's a lot. So it deals with the potential energy, the gravitational potential energy. Okay. All right. So any questions? In the textbook, of course, they use 9.8 meter per second square, not 10. Yes.
So tomorrow there's no lesson, right?
I cannot hear you, Max.
Tomorrow there's no lesson, right?
No, tomorrow is Good Friday.
Okay.
You should go on the web and attend to a virtual Good Friday ceremony.
Okay. But do you also have like the extra help sessions in the afternoon as well?
Yeah, we'll do this. Yeah, it's gonna be on Friday, but not now.
Okay.
But next week.
So you'll
It'll
send the
be
email
on
out,
Friday.
right?
Yeah.
Okay.
I'll let you know more about this.
Okay. Thanks.
Whose dog is this? Is this your
Oh
dog,
no,
Matt?
no. That's my mom cutting stuff for cooking.
Wow. Oh, wow. She's very violent there. Whew. Okay. So okay, guys. So unless you have like any questions here, so I want to wish you a happy Easter on the Sunday. So I wish you all the best, you and your relatives and your loved ones. Have a very happy Easter. And don't forget that tomorrow is Good Friday. So this is a day of abstinence. It means like you cannot eat meat, as well as a day of fast. So you're not supposed to eat like too much. All right. So just to commemorate like the fact that our God, that Jesus like died on the cross for us. So if you don't have any other questions here, if you do have questions, just hang on. And if you don't, I guess I'll see you like on Tuesday, because Monday there's nothing. It's Easter Monday, so there won't be any session. Okay. All right. So bye bye. Okay.
Happy Easter.
Happy Easter.
Happy Easter.
Okay. Don't eat too much chocolate.